Warm greetings to all of you. It is a pleasure to come your way for this special tutorial session. And this tutorial session has become very necessary in order to assist you to be able to plot the stress strain and or load extension graph. And this is Strength of Materials 1 tutorial session. Indeed, this tutorial session is very crucial because plotting graph in strength of materials, though is similar to what we have done in mathematics, is not the same because the values are generally decimal values compared to mathematics, where most of the time the values are round figures or whole numbers. And so where you have decimal values and attempting to choose your scale and plotting with accuracy can face some form of challenge. And so today, just stay with me, and I'm going to demystify all these challenges. If you are an engineering student, a building student, and you have challenges in drawing graph, this is your last stop. And just stay with me within the next few minutes, and I'll be able to help you out. So basically, the objective of this, as I mentioned earlier, is to help you on how to plot a graph. In fact, this approach can be used for any kind of graph, but specifically, I'll be using a load extension graph or curve to demonstrate all that I'm about to teach you. And at the end, you should be able to plot a graph in pencil. Indeed, we have computers to plot graphs, but let us not be deceived. Computer was created by a man, and that matter, the brain. So you should be able to understand how the graph is plotted, because the computer one is more or less like a black box, but it should be able to plot the graph on your own. And then also you should be able to interpret. So the outline will be introduction, basic techniques in plotting a graph, some illustration, and I will show you a sample calculation for plotting. And then I'll finally assist you to plot the graph, and then you see how easy this can be. Now, this tutorial session will be focused on techniques for plotting a load extension curve and a stress strain graph. So the main lecture on stress strain relation is covered in separate lecture, which is lecture 2. This can be obtained upon request. So I've done a very comprehensive lecture on stress strain relations, and in that lecture we've learned a lot of stuff about how this stress strain graph came about, the various tests that resulted in this, and then how to estimate or evaluate various important parameters like the modulus of elasticity, stress, yield stress, and so forth. And so that has been done already. And today's case is not focused on that. Today is about helping you to draw a graph. So hence, a typical lab data will be used to illustrate the basic technique required to plot the graph. Okay. The same technique can be adopted to plot any type of graph, whether stress strain graph or whichever. But remember, if it is stress strain graph, then you have to calculate the stress using force over area or original area of the bar, and then calculate the strain, change in length, over original length. Is that right? And then you have to select an appropriate scale based on the values you plot. If it is a load extension, you are going to plot the load against extension. But if it is stress strain, you are going to plot stress and strain. So make sure your scale is based on the actual values you'll be plotting. And what are the basic techniques in plotting graphs? Some few guidelines. You have to decide on the type of graph sheet, whether it's a plain Cartesian graph sheet, semi-log, log-log, polar graph sheet. You need to know the type. But in this tutorial section, we using plain Cartesian graph sheet, which is the standard graph sheet you see usually on the market. And you should be able to determine suitable scale for the X data and the Y data. Your scale should fall within the lower bound value and upper bound value. So lower bound value will give you the biggest graph, and the upper bound value will give you the smallest graph. And always select values close to the lower bound value. I'm going to explain that in detail, so don't worry. So for high accuracy in plotting your graph, plot a graph using boxes instead of the actual values. This too is, in fact, the basis for this tutorial session. The rule of thumb is that the graph must cover more than half of the grid in both horizontal and vertical directions. You can't plot a graph and the graph will take less than half the space of the paper you are using. It must take more than half. Okay? It shouldn't take the 100%, but we want your graph to cover more than 50% of your graph sheet. So this you see here is basically a standard graph sheet. Okay? And I'll be talking about some large squares, small boxes. So if you take this particular direction, okay, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so you have 10 large squares in this direction, and then vertically, if you count them, okay, you have 12 large squares. Essentially, this is the standard graph we have on the market. Okay, so this is if the graph sheet is positioned in a portrait direction, and then if it is in a landscape, then in the landscape horizontally, the 12 large boxes will be on the horizontal, and then on the vertical will be the 10 large boxes. Okay, all right. So to further throw light on that, if I say large boxes, then I'm talking about what have been marked with the red boundaries. So every large box has been subdivided into 10 small boxes. Okay. So if I say small box, I'm referring to something like this. Is that right? So every large box, both way, have been divided into 10 small boxes or 10 small parts, equal parts. So if I say large boxes, I'm referring to this. So essentially, for a graph, this dimension is actually 2 centimeters. Okay, and then this dimension is also 2 centimeters. So you notice that within the large box, there is a middle part of it. Can you see this line? So this is 1 centimeter, 1 centimeter. But just understand that if I'm referring to large box, I'm talking about 2 centimeters by 2 centimeters. Okay? And the small box is the 10 equal subdivision of the large box both ways. I hope that is clear. All right. Now, if you want to plot your graph, one of the important things you have to do is to select your scale. So, well, this is a stress strain or load extension curve. So we have values for X and then values for Y. In other words, you have the load and extension. So the load is plotted on the vertical, which is the Y-axis. The extension will be plotted in the X-axis. So the first thing you have to do is calculate the lower bound value. Okay, and the lower bound value is simply changing the X. We are talking about the X data, right? So the formula is changing X over number of last squares in the X direction. What is changing X? So you have to look through the X data, okay? Look through all the values, pick the minimum, and then pick the maximum out of the given values. And the max minus the minimum value is what will give you the change in X. Is that right? And when you do this calculation, we call it the lower bound value. And the next thing is find what is called upper bound value by multiplying your lower bound value by 2. Okay? When you do that, you get the upper bound value. This lower bound value and upper bound value are very important parameters to be using to decide on our scale. Is that okay? Then choose a systematic value between the LBV and UBV and use this value as the scale in the X direction. Okay, so let's say if we calculated and then we had a lower bound value of, let's say, let's say 20.1. This is a lower bound value. And then we have an upper bound value of, let's say, 50.8. So which means that between 20.1 all the way to 50.8, you can select anything within that range as your scale. Okay, so you need to make sure the numbers you are selecting are within this range, and of course, it should be easily divisible by 10. Okay, because the graph is divided into 10 parts. So if you make it easily divisible by 10, you get a very high accuracy in your plot. So this one I can say 25. Next one I can say 30, 35, 40, 45, and then I can even take 50 because this is 50.8. So with all these values, you can select any of them as your scale. And if you want your graph there, as I mentioned earlier, the lower bound value will make the graph very big to occupy the entire area. And the upper bound value will make the graph just about 50% of the graph sheet. So always try to select values close to the lower bound value so that you have a good and a big graph in there. Okay, so once this has been done for the x-axis, you have to do similar for the y-axis. And here, as you can see, the change in y is equal to maximum value minus minimum value. So just go through the y data, okay, and then look for the minimum value and then the maximum value. So if all your values are positive, it is important to rather select 0 as your minimum value, even if there's no 0. Is that okay? But if there are negative values, then make the negative your minimum value, and then the positive your maximum value. But if there's no negative value, try to use 0 as your minimum value. Okay. So in a similar manner, this calculation also have to be done. And then you can use this one to select the scale for the y data. Then after you have been able to determine the scale, okay, you have to now determine the value of each small box. You remember I mentioned large box or large squares and then small squares. Is that right? Okay. So now, if you have determined the scale, okay, let's say every 2 centimeters is equal to, let's say, 10 kilonewton. That's the scale, let's say, we have selected. If this is the scale, our focus is this value, right? So how do we know the value of each box? This 10 kilonewton is given to every large box. Okay? If this is 0, the next point is 10. So this subdivision of 10, what is the value of each of these small subdivisions? It's simple. You take this scale value, okay, or the interval, you divide by 10. Number of small squares will remain 10. Is that right? So take that value and divide by 10. So 10 over 10 will give us 1. So it means that each small box is 1 kilonewton. Okay? So you do same for the this one in the y direction. Okay? You do same for the y direction. So that if I take, let's say, x direction, I know one box is equivalent to, let's say, 1 kilonewton. And if I take x direction, I know one small box is equivalent to, let's say, 1 millimeter or 2 millimeter. And that is, now your focus for drawing the graph will now be these two values you are going to establish. Okay. So after this, you proceed in plotting your graph. So you now pick the actual values you are going to plot and divide by this, the value of the small box in either way, and then you now plot in boxes instead of the actual values. And when you're able to do that, you'll be able to have a very high accuracy in plotting and high precision also, even with plotting in pencil. Right. So let's see a typical illustration. So I am using this load extension readings as an illustration to demonstrate how this graph can be plotted. All right, so these values have been given, okay? So the first row is load in kilonewton, and the second row is extension. So you start with 0, 45.05, mark 2. So all the numbers in the first row are loads in kilonewton, and the second row are all extension in millimeters. So let us look at the, for example, if we take the load axis, in our graph, the load will be plotted in the x-axis, y-axis, and then extension will be plotted in the x-axis. So for example, if we take the y-axis, what is the maximum value and minimum value? Well, minimum value is 0, okay? But if we go through these values all the way to the end, okay, you notice that the maximum value is 250.25. You get it? So we are going to use this and this to calculate our change in y. Again, if we take the x-axis, minimum value here is 0. And if we're able to go through, we will notice that the maximum value is what? 4.94. So let's keep these numbers. We are going to use them. Y-axis, which is the load axis, minimum is 0, maximum is 250.25, and then the x-axis extension minimum is 0, and the maximum is 4.94. Okay, so let's keep these values. Right now, so essentially, this is what has been done. Now, you have to make an important decision. Because of the nature of our graph, okay, the usual graph sheet is like this, right, which is the portrait. But because of the nature of our graph, we will turn the paper like this, which is the landscape. If this is the case, you remember we counted along this line is 12 boxes. And then along this line is 10 boxes. Let me also inform you that the graph you are using for the plotting, make sure you count these boxes yourself So some of the graph sheet may be different from the standard so that you stick to the parameters of your graph sheet. Is that right? So if that is the case, and remember the load is going to be plotted on the y-axis and the extension on the x-axis. So if we are calculating for x-axis, which is the extension, we'll use 12 boxes. Is that okay? And then the y-axis, we are going to use 10 large boxes or large squares. Okay? So that is the important thing you have to first decide on. So now, let's see how we'll be able to deal with our scale. So we want to determine the scale in the x direction. Is that okay? So in the x direction, we have to calculate our change in x, which I told you is maximum value minus minimum value. Okay? And remember, this one is the extension. In the previous slide, we established that the maximum is 4.94 and the minimum is 0. So when you subtract 0 from this value, you get 4.94. Then the second step is calculate the lower bound value. So the lower bound value is change in x over number of large squares in the x direction. So because we have turned the graph this way, you remember? This direction, we have 12 large squares. Is that okay? So we'll take this change in x, we divide by 12 large squares, and our answer is 0.412. So take note of this value. We are going to calculate our upper bound value, okay, which is just 2 times the lower bound value. Okay. So after we are done with the lower bound value, we'll deal with upper bound value. So yes, multiply the lower bound value by 2. Okay. So that will be 2 times 0.412, giving us 0.824. So now you select your suitable scale. So you see this simple thing I've done here. The lower bound value is 0.412 and the upper bound value is 0.824. So your scale you're going to select should be within this range. And as I said, don't take complex numbers because any number greater than 0.412 and less than 0.824 are all possible. But don't choose certain values that will make plotting difficult. So make sure you choose simple rounded figures. Is that right? And that's why I've just said 0.45, 0.5, 0.55, 0.6, 0.65, 0.7, 0.75, 0.8. They're all within this range. And as I said, lower bound value will give you the biggest graph ever. And the upper bound value will give you the smallest graph. So if you are selecting, try to select close to the lower bound value so that your graph will be big. So in this case, you can either decide to take this, any value here, but I admonish you, take value close to there. So, well, you can take 0.45, you can take 0.5, 0.55, 0. Anything here, okay? But I am adopting 0.45. Well, somebody may adopt 0.5, but that's a matter of preference. So I'm adopting 0.45. If that is the case, you remember the last square is 2 centimeters. So it means my 2 centimeters is equal to 0.45. This is the 0.45, right? And that will be the scale for the x-axis. Very, very simple, okay? So it means 2 centimeters is equal to 0.45 millimeters because that's the extension axis, okay? Very simple. So this that we have done, you do similar thing for the y data, okay? What do? You calculate change in y, or if you like a recap of we first calculated change in x, and then we calculated the lower bound value by dividing the change in x by the number of large squares in that x direction. And then calculate the upper bound value by multiplying lower bound value by 2. And then you select a reasonable number within that range as your scale, okay? So if we go to the y direction, in the previous slide, we established that the maximum value is 250.25. Do you see? And the minimum was 0. So This difference will give us 250.25. Then proceed to calculate your change in lower bound value, change in y over number of last squares in the y direction. And based on how we have turned our graph, and the graph I've shown you, last squares in the y direction will be 10. And this will give us 25.025. Okay, so take note of this number. Then the next step, we're going to calculate our upper bound value, which is the lower bound value, okay, which is the lower bound value times 2, and that will give us 50.05. So your scale is between LBV and UBV, is that right? So this is the lower bound value, this is the upper bound. Any value within can be selected as your scale. This is 25. You can say 26, 27, 28, 29, 30, 31, but just select reasonable round figures, which can easily be divisible by 10, so that you don't get too much decimals, value for one box. Is that right? So from 25, I move to 30, 35, 40, 45, 50, and so on. Once again, I'm selecting 30, okay? You may decide to select 35 or 40, but like I said, if you select close to the LBV or lower bound value, your graph will be big enough. Okay, don't select too close to the UBV because the graph may occupy everywhere. Is that right? Good. So if that is the case, now I've selected 30. It means that my 2 centimeter, which is the last square, is equal to 30 kilonewton. Okay, so what did we do? The x-axis, we had 2 centimeters is equal to 0.45 mm. And then y-axis, 2 centimeters is equal to 30 kilonewtons. Very simple. In fact, all that we have done now, you can even do it without writing anything. You can just simply use your calculator to evaluate it. And within the next 2-3 minutes, you should be able to find your scale. Don't jump into drawing. It's important to find a reasonable scale so that you'll be able to plot your graph with ease. Okay? Good. So now we have been able to find a scale. The next thing we have to do is to find the value of each small box. The value of each small box. So remember, in the x direction, our scale is 2 centimeters is equal to 0.45 millimeters. And then let me add this one. Scale 2 centimeters is equal to 30 kilonewtons. Okay? So if you want the value of, if you remember, I said one large box like this is subdivided into what? 10 equal parts. Is that not so? And then this side has also been subdivided into what? 10 equal parts. But because we are dealing with the x direction, we deal with the horizontal. Okay? So what I'll do is that this interval I've selected, I'll just take the interval divided by the 10 small squares, right? So which means that each of the small square, okay, each of the small marking, okay, is 0.045. So it means this, if this is the origin, it will be 0. The next one 0.045. The next one is 2 times 0.45. The next one 3 times, and so forth. By the time you get here, you will land on 0.45. Then in the y direction, we also say take the scale interval for y axis, okay, and then divide the number of boxes in each number of boxes in each. They should be each large square. Is that okay? Because with our scale, we selected 30 at the interval. We take 30 again is divided into 10 small boxes, and that will give 3 kilonewtons. Once this has been done, we are completely through with all that we need. Now we've been able to find a scale we have also been able to find the value of each small box. So to summarize, in terms of the value of each small box, in the extension, which is the x-axis, okay, 0.045 mm per small box. And then in the load axis, 3 kilonewton per small box. Is that okay? So it becomes very simple now. If I now want to go and plot the graph, I am going to plot in boxes. So whatever value in the load axis, okay, I'll pick the value and divide by 3. And if I pick that value and divide by 3, whatever answer I get is in boxes. So I'll just be counting boxes and be plotting. And if I want to plot the x data, I'll take the value divided by what? The value of one box. And whatever I'll get, the answer is in boxes. And so you'll be plotting in boxes instead of the actual value. So now we have been able to establish all this. Let us see how you'll be able to now plot that graph with ease. So again, I've brought the values here, okay? This is the y-axis, and this is the x-axis, okay? So if I take the load, I can take these first two numbers. Of course, all of us, we know that that one will give you 0 boxes, isn't it? Then I'll take the next one. I'll take the load. You remember the value of each small box is 3? So I'll take the load divided by 3, okay? So this answer I get now is what? Boxes. And then I'll take the corresponding extension and divide by the value of each small box. I'll now get 2 boxes, okay? So you take each of these, before you plot them, take each of these values, divide by 3 kilonewton, which is the value of each box. And whatever you get, remember, is in boxes. It's in boxes, okay? Whatever that you get is in boxes. So, for example, what has happened here is that, look, in one large box, as we said, it has been subdivided into 10 boxes. Okay, this may be less, but that's fine. So this is the x-axis. Is that it? So if this is the x-axis, and let's say now with the, for example, this one 0, 0, so it will be here. Then if I take the second one here, okay, this x-axis is what? 2 boxes. So I'll just count. This is 1 box, 2 box. So it's here. And then the y, this one, 2, will be counting. So you see that by the end, you get 10 boxes. And then you keep counting. Maybe the 5th one will be here. So what I do is this one, and then this one, where they meet. Okay? So remember, if you are plotting a graph with pencil or manual, you either use this one or something like this. Okay? These are the best way. This is not allowed. This is also not good. Okay? So at the end of the day, if you have just a dot, you have a circle around. So when you are plotting, it should pass through the dot. But if you deepen it, how do you know whether it is here or here? You know, so we don't do that. You use either this or just a simple cross like this. So this is the preferred. Is that okay? So note that all these preliminary calculations, you don't need to show working before you start drawing your graph. It's just a rough work. Is that right? It's a rough work you have to do before you start your graph, you know. So please, you don't need to show working anywhere. It's just a rough work that will be able to help you to plot your graph. That's all. Okay. So Once you have been able to establish the value of one box, you take the actual values you are going to plot, okay? And then you divide by the value of that box. And remember, the answers you are going to get, they are all in boxes. They are all in boxes. Is that right? Okay. Now, this is a continuation of the calculation, okay? So you see that all the load values, if I pick the load value, I divide by the value of one box, 3. And this is given at 32.7 boxes. If I take the next one, I divide by 3, I get 49.1 boxes. Okay. So now it's important to note here. Let's say you have a big box. Okay. So let me say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So this is the big box. Is that okay? Subdivided into 10 parts. Now, if you get 2 boxes, it means this is 1 and this is 2. So it will land here. If you get 3 boxes, it's going to land here. Anything point something means it's less than 1 box, right? So if you get, let's say 49.1, between 2 boxes, between these 2 lines, 0.5 is in the middle here, okay? So you have to just use your judgment to be able to locate 0.1, 0.2, 0.3. And as you know, 0.5 is in the middle of the small box, you know. So anything point something means less than 1 box. So use your judgment to decide where it will be. And that margin of error is very small. Okay. So if it is 0.5, I would have landed in the middle of this box. So 0.6 would be a little bit away and like that. Is that okay? Good. So in the next page, once again, I've taken few of the values. So all that I'm trying to illustrate to you is that you take each of these values and divide by their equivalent value of a box. Okay? Now, when you do this, remember that when you are now plotting, you'll be plotting this and this to represent this value. Is that okay? You no more plot this directly. You are going to plot this one and this. So you'll be plotting boxes, which will be equivalent of the actual values. Okay? So as I told you, if it is stress strain graph, for example, then remember that you are not going to use these values directly. You must calculate your stress and calculate your strain and use that one to get the scale. Is that right? And then after that, you can get the value of each small box, and then subsequently you can proceed up to this stage. So let's see. First of all, I've attempted to zoom this one. Okay. So the first value is 0, 0. Okay, which of course we know is the origin here. Is that right? And then let's see the second item we calculated is what? 15 boxes in the load axis and 2 boxes in the extension axis. So 15, 2. So we know, okay, 15 in the load axis and then two boxes in the x axis. So you remember from here to here is 10 boxes. This is also 10, 20, 30. Okay, so this is 10 and 15 will be in the middle here. Okay, 15 will be in the middle here. So from here, you just have to draw a line. And then this is 0, right? This is 1. This is 2. Is that not so? So you draw another line. Please, you may not necessarily need to draw this line on your graph. Okay? Don't draw this line on your graph. Just understand that where you locate the 2 and the 15, the two of them, okay? The two of them, where they meet, then you have to mark, okay? And as I told you, you use either this mark should be at the point where the two are going to meet, okay? Or you use this, please. These are the preferred. If you are drawing the graph with computer can do many things irrespective of the shape. But in terms of we drawing the graph manually, you do what the eye can easily locate the right point. Okay. Then let's see again. You see the next one here, which is the third point, we have what? 32.7 boxes in the y-axis and then 4.2 boxes in the x-axis. Okay, 32.7, 4.2, 32.7, 32.7 boxes, 4.2 boxes. This is the x and this is the y. Okay, so we know that up to here is 10 boxes. This is 20. This is 30, right? So 32, 31, 32. 0.7 means less than a box. So above the 5 somewhere here, right? So I can have this. And then the 4.2. We know this is 1 box, 2 box, 3 box, 4 boxes here. 0.2 somewhere, not up to 5. So this one, okay, well, my line is not straight. And this, where they meet, okay, then you just mark that point. So you are going to do this again and again until you finish plotting all the points. Okay, so as per the stress strain graph, okay, so you see that what you can see here, after you have been able to establish your scale, you must graduate your graph. Remember, it's a load extension curve. The load is on the vertical and the extension is on the horizontal. So you just take your calculator and then you divide as you draw, or use pencil to indicate the boxes, or either on the question or whichever paper you have. And then the first one, can you see? That's 0, 0, so it's easy. And then this, you draw this point as I've illustrated in the previous slide. Then this point to boxes, you take. Boxes, you take. Boxes, you take, like this. And you do this until you are done for all the points. Beautiful. So this vertical and horizontal lines I'm just using that to guide you. But on the graph, these lines are right there. So just use your rule and locate them, and you may not need to draw the vertical and the horizontal line. The most important things that you need are these markings. Okay. Now, this is a mass steel bar. So typically, for the stress strain graph, up to a certain point, it will be a straight line. So you put your rule on it from the origin up to a certain point, say somewhere here, a straight line, and then the remaining become a smooth curve all the way to the end. And that one you have to do, and then you get something like this. Beautiful. Okay, so this makes plotting so simple and so easy. You don't need to struggle, and you are plotting with boxes. And as you can see, because we have selected a full scale, the maximum value is here. Even 1 box is left. Do you see? And then the maximum, you see that one was 250 something, and I have 270, and even 1 box is left. Yes. So if I have my graph covering almost 90% of my graph sheet. That's a good thing. Is that okay? Yes. So this, remember, is a landscape. It's a landscape. So when it comes to the evaluation of the Young modulus and the other properties, as I said, it's in a different lecture. If you wish to have it, you can just send a message to me, and then I will be able to provide that for all to get access to. Okay. So what did we do? So the final graph, which this one was plotted with a computer, okay, this is how I look. So what did we do? What we did was that we established a scale for plotting a graph. And in this case, I used the load extension lab data to do this. And you need to establish for X direction and Y direction separate. So if I take X direction, I have to look for the minimum and the maximum value within all the values given. Then I have to calculate my change in X, which is maximum minus the minimum. Then I have to calculate the lower bound value by dividing change in X over the large squares. So if my graph, the graph sheet I use on the horizontal, I have 12 large squares. So I divide by 12. And then I'll get the lower bound value. So the upper bound value is simply 2 times the lower bound value. Then the scale you are going to choose will now be between the lower bound value and the upper bound value. And I said, try to choose a value a little close to the lower bound value so that your graph can be big enough. Make sure you don't select complex values. See, simple, rounded value or just simple value so that when you divide by 10, it is very easy and simple. So don't take too much complex decimal places. You have all the right to select. So select the best first. So you do same for the y-axis. After you have established your scale, you take your scale value, which is the interval, divide by 10 to get the value of each small box. And now if you are plotting, you take the value, divide by the value of that small box. And remember, the answer you'll be getting will be in boxes. So just be counting the boxes and use it to plot. Isn't that beautiful? So this technique is very simple and can be adopted for plotting any type of graph. The steps involved should be considered as preliminary steps only, just to help you establish your scale and plot your graph with high accuracy. You can simply use your calculator to get the scale without necessarily writing it down step by step as presented in it. I am kind of teaching you how to do it. And so that's why I have to make this long presentation. Otherwise, within 5 minutes or less, you should be able to establish your scale and the value of each small box and begin to plot. Look, and this approach can let you plot the graph within a very short time because you are plotting, you are not now going to see what is 0.45 millimeters on the graph sheet. No, you just count boxes and so easy. And remember that the boxes as we're plotting, if your answer gives you 50 boxes, always start counting from the origin. Is that okay? Always start counting from the origin. So they have 10, 20, 30, 40, 50. So always start counting your boxes from the origin. That is a simple approach you can adopt. Okay, good. And if you want to plot your graph with high accuracy and precision and hassle-free, then I recommend this approach for you. Okay. So I hope that this is able to give you some leverage and some knowledge and skills to be able to help you plot any kind of graph, whether decimal or rounded figures with ease and with very high accuracy. Okay. It's a pleasure to have you, and this is the end of this tutorial session. Thank you. If you have any question, you can drop your question down in my message box. And again, if you want further assistance, don't hesitate to contact me. I'm Engineer Samson Aguje. Okay. So just drop the message in the message box. And don't forget to subscribe to this channel. And I'm having good plans to give you very good content, especially if you're a student, engineering student, construction student, and in terms of strength of materials and structural design, this is your last stop. Thank you very much and have a blessed time. Bye.